Next, let's look at a car accidents example. And so here we define the random variable A to be the number of car accidents college students have been in. And so first of all, we convert the frequency table into a probability distribution. And you know how that works. We add up all the frequencies, and then we divide each frequency by the total number, and that gives us the probability. So we add up all the frequencies, that'll be 50. So then the probability here would be 27 divided by 50, 27 divided by 50, or 0.54. Here we have 15 divided by 50, that's equal to 0.30, etc. 0.30, then 0.10, and 0.04, and 0.02. And we add up all the probabilities, and they add up to 1.00 as expected. And now, again, continuing with this example, where A is the number of car accidents college students have been in, we find the mean by using the formula we looked at previously. And so the mean turns out to be 0.7 car accidents, and the standard deviation turns out to be 0.94 car accidents. Now, the usual number of car accidents are between the mean plus 2 standard deviations, so there would be 0.7 plus 2 times 0.94, and that's equal to 2.58 car accidents. And then the mean minus 2 sigma would be 0.7 minus 2 times 0.94, and that's minus 1.18 car accidents. And since we can have a negative car accidents, we say between 0 and 2.58 would be usual for the number of accidents we would expect for college students to have been in. So then the next question is a student who has 4 car accidents unusual? Well, if it's between 0 and 2.58 be considered usual, then obviously when someone has 4 car accidents, that would be unusual. So that is unusual. The next question is, find the probability a randomly selected student has been in less than 2 car accidents. So here, P of A less than 2 means the probability of 0 accident plus the probability of 1 accident. So 0 plus 1 would be 0.84. 0.84 for probability of 0, 0.54, probability of 1 being 0.30. So together it's 0.84. And then the probability of at least 1 accident, so in other words, the probability of A being greater than or equal to 1, we could add up all the probabilities for the probability of 1 plus the probability of 2, etc. But it would be much smarter to say, well, the probability of at least 1 would be 1 minus the probability of none. And since the probability of no accident is 0.54, it would be 1 minus 0.54, which is equal to 0.46. So in other words, the probability of at least 1 accident would be 0.46. So as you can see, this consideration that if it's at least 1 is equal to 1 minus the probability of none, it's usually much more convenient and faster than to add up all the probabilities from 1 plus until you get to the end. Now the formula to calculate the mean of a probability distribution was equal to the summation of the random variable times its associated probability. But that is the same as the expected value. Again, it's a summation of the random variable times its associated probabilities. Okay, so we've done this a few times before. So it's just, again, an observation we made a little while ago. So the expected value can then be used to predict long-time or long-run profit or loss. So let's look at an example here. So let's say at a raffle, 1,000 tickets are sold at $2 each. There are 3 prizes for $500, $250, and $100. If you buy 1 ticket, what is your expected profit or loss? Well, if X is the profit, the profit amount, then when you buy a 1 ticket, then for 1 you have only 498 because you already spent $2 to buy the ticket, and here the probability is 1 out of 1,000, and there would be 0.001. Okay, then for the other prize of $250, so you have 248, and the probability is also 1 over 1,000, so it's also 0.0001. And for the other one, for the $100 ticket, you have $98. That would be a profit, and the probability again is 1 divided by 1,000, or 0.001. And then the probability of losing $2 minus $2 would be then the difference, or 997 over 1,000, and that's 0.997. That's a 7 here at the end. 0.997. Okay. So then the question is, what the expected profit? In other words, what can you expect to gain or lose? The expected value would be the profit of the random variable times its associated probability. So there would be 498 times 0.0001 plus 248 times 0.001 plus 98 times 0.001 plus, now it's a -2 because that's what you spend on buying a ticket, times 0.997. So we multiply the random variable times its associated probability, and we take the sum of all of this, and when we do that, that comes out to minus $1.15, of course. And what that means is that you can expect to lose an average of $1.15 for each ticket you buy. Now, what does it mean in reality? Well, it doesn't mean you lose $1.15 when you buy a ticket, because you can't, because you spend $2, so you either win or lose. But what this means that in the long run, when you repeat this procedure many, many times, you can expect to lose $1.15. Let's look at another example. Here we look at a frequency table where for a period of 250 days, a fire station kept track of the number of emergency calls they received by the station each day. So they received 0 emergency calls for 12 days, and etc. So the frequencies add up to 250 days, 250. We're told that's equal to 250. So then here we have our random variable 0, 1, 2, 3, 4, 5, 6, and 7 calls, and then we divide the random variable by the total number of the frequency, and so 0 divided by 250 would of course be 0. So 0 divided by 250 is 0, and so we fill out the table for each of the values of the random variable. Oh, I'm sorry, this is okay. And so as we divide the frequencies by the total number of 250, so 12 divided by 250 is equal to 0.048, etc. 29 divided by 250. So now we have the associated probabilities of 0.116 and then 0.344, and then for 3 calls would be 0.296, and 37 divided by 250, that would be equal to 0.148, and then 6 divided by 250 would be 0.024, and then 4 divided by 250 would be 0.016, and then here finally we have 0.008. So here are our probabilities. So then when we use a formula for multiplying the random variable times the probability and adding up all the sums of the random variable times its associated probabilities, then the mean comes out to about 2.56 calls. Emergency calls, that is. And then for the standard deviation, it would be 1.25 calls. So then the usual number of calls would be the mean, or 2.56, plus 2 times 1.25, or 5.06 emergency calls. And then for the lower limit would be 2.56 minus 2 times the standard deviation, 1.25, and that's equal to 0.06 calls, emergency calls. So then between 0.06 and 5.06 would be the usual number of emergency calls for this particular fire station. That's what you can expect on average per day. Let's look at another example that says the cup holder in your car has leftover coins, and it currently contains 12 dimes and 5 quarters. You pick 2 coins at random without replacement, and X is the value of the 2 coins you're holding in your hands. What is the highest value of 2 coins you could be holding in your hands? Well, the highest value would be if you had 2 quarters, so the highest value would be 50 cents. And what is the lowest value of the 2 coins you could be holding in your hands? Well, that's if you picked 2 dimes or 20 cents. And then, is there any other possible value of 2 coins from the cup holder? Well, that's the only dimes and the quarters. The only other possibility is a dime and a quarter, so you have 35 cents. That would be the other possibility. Okay. So, now let's make a frequency distribution here, and let X be the value of the 2 coins you have selected from this cup holder. So it could be 20 cents. It could be 35 cents, and it could be 50 cents. So to visualize the distribution here, let's do a tree diagram, and let's suppose you start out with a dime, and then the other possibility is you get another dime, but remember this is without replacement. So the first probability is 12 divided by 17, and then the next one would be 11 divided by 16. So the probability of winding up with 2 dimes is 12 divided by 17 times 11 divided by 16, and that's equal to 0.4853. Or you pick a quarter once you have the dime, and here you have a probability of 5 divided by 16. So then that probability is 12 divided by 17 times 5 divided by 16. Okay. Now, here's what happens when you start out with a quarter. So here you have a quarter. And of course, that gives you a probability of 5 divided by 17. And then you have another quarter, a quarter here. And there would be now 4 divided by 16, because again, it's without replacement. So then to wind up with 2 quarters, the probability is of having 50 cents. There would be equal to 5/17. 5/17 times 4/16, and that's equal to 0.0735. So that's a probability of having 50 cents. This was a probability of having a dime and a dime, so it's a probability of 20 cents. And then here we have the probability of a dime and a quarter, but here we have the probability of a quarter and a dime. And that, of course, would be 12 divided by 16 here. And so we divide, so we have 5/17 times 12/16. So that together is equal to 0.4412. And so that's a probability of having 35 cents. So we can fill in our probabilities for the various amounts. So it would be 4853, and then to have 35 cents would be 0.4412, and then to have 50 cents, the probability would be 0.0735. And when we add up these probabilities, they add up exactly to 1.000 to all the decimals. So in other words, what you can say is that the expected value would be then the multiplication of the random variable times its probability. So when we do that on the bottom of the page, I hope you can see that okay. There would be the expected value E of x, or what you expect to have in your hands, would be 20 cents times the expected times its probability, 0.4853, plus 35 cents times 0.4412, plus 50 cents times 0.0735. And when you add up all these products, you get 28.8 cents. Now that's on average. And what it really means is that you obviously will never have 28.8 cents in your hands. That's impossible. The only possibilities are 20 cents, 35 cents, and 50 cents. But if you reached in there many, many times, on average, you would have 28.8 cents. So let's say you pick that, you repeat, choosing two coins, you did it 100 times, then the average would be about 28.8 cents over long time, on the long run.